Welcome to Maths for All. I'm Aisling Flynn. This is higher level. Today we're looking at statistics, estimating population proportions. Okay, so this topic, it's very similar to the previous one on population means. Okay, it's the same strategy, but there will be a different margin of error for population proportion instead of the means. Okay, so because populations are often very big, we often have no way of knowing exact proportions. So today in this video we're dealing with proportions, okay, not means. So how much of the population will vote for candidate A, for example. Okay, so it's a proportion, not a mean. For that reason, because we often cannot survey a full population, we use samples. Samples can give a sample proportion, which is called p hat, and this is used as a point estimate, so an estimate to give an idea. However, we must give some indication of how good this estimate is, i.e. what's its accuracy. To do this, in a little while we will construct a confidence interval. In our course we construct a 95% confidence interval, and this means that if we constructed this interval 100 times by taking samples, that the true population parameter p would be expected to lie within the interval 95 times out of 100. Okay, so standard deviation. Individual samples can give different results. We saw that when we looked at sample variability. But if enough samples are taken, all of the sample parameters, so all of the p hats, would form a normal distribution around the population parameter p, so around the real value. The standard deviation of this distribution is found on page 34 of the Formula and Tables books, and it's given as this. So it's the standard deviation of all the p hats, and that's how you would calculate it, where p is the population proportion and n is the sample size. Okay, so that's on page 34. So margin of error. We can use the standard deviation from the previous slide to get a margin of error for our confidence interval. Okay, the margin of error for the population proportion at the 95% confidence level at higher level is given by E equals 1.96 by the square root of p times 1 minus p over n. So some of this is familiar. The 1.96 we saw in the previous video refers to the z-score. That is 2 standard deviations above the mean, and that's what gives us the 95% confidence. Okay, and you'll recognize from the previous slide the square root and the expression underneath it as the standard deviation of all the p hats. Okay, and that was on page 34, recall. So that gives you your margin of error, where p is the population proportion and n is the sample size. However, we rarely know the population proportion, so it's rarely possible to survey a full population. So we may need to use the sample proportion as an approximation. So what happens here is that p hat replaces p when it is not known. Okay, it's an approximation, but it's not too bad. Okay, so just be aware of that. Now let's construct our confidence interval. So the 95% confidence interval for the population proportion p. So where is p? P would be between the sample proportion minus the error and the sample proportion plus the margin of error. Okay, we've seen that before. And filling in for the error, this is what we get, and we use this version when p is known. And when we don't know P, which is often the case, we'll use P hat instead, okay? It's a best approximation when P is not known. All right, here's an example to show how that's done. In a survey of 1,000 voters, 690 said they voted in a recent general election. Voting records show that 63% of eligible voters actually did vote. A. Find a 95% confidence interval estimate of the proportion of people who said they voted. And B. Are the survey results consistent with the actual voter turnout of 63%? Okay, so how to do our interval? Well, our interval usually consists of the population proportion between the sample proportion minus the error and the sample proportion plus the error. So we need to make sure that we have all these values. So firstly, our population value is given by voting records. So in this case, we do know an actual population proportion. Okay, so 63% the record shows actually did vote. So 63% is written at 0.63. Okay, now we have to find P hat, the sample proportion. So to do that, we'll use the number in the sample and how many said that they actually voted. So 690 out of 1,000 said they voted, which is 0.69. Okay, and also we need to calculate the margin of error. So for proportions, we saw that we have a new definition of margin of error. Okay, it's 1.96 by the standard deviation of samples, which you'll find on page 34, and there it is there. So our first job will be to calculate that. So let's do that here. E equals 1.96. Now in this case we do know the value of P, so we can use that in our calculations. And N is 1,000. And what you get is a 0.0299 and some other figures, which we will round to 0.03 or 3%. Okay, now we're at a position to construct the interval. Let's fill in for P hat, which is 0.69 minus our error, and then we'll have our P hat plus our error. Okay, and that gives me 0.66 or 66% as the lower limit of the interval and 0.72 as the upper limit of the interval. There's the answer for part A. Now, what does that say? It says that according to the sample, the true population proportion should be between 66% and 72%. Now, we know for a fact that it's actually 63%. So part B asks, are the survey results consistent with the actual voter turnout? And the answer is no. 63% does not lie within the interval. Okay, so the sample chosen does not reflect the real population. So what might be a reason for that? It could just be random, in which case you'd have to carry out many more questionnaires and take many more samples. And if you took enough samples, well, then it should agree with 63%. Or the other possibility is maybe some of the 690 people were not telling the truth. Maybe they didn't vote at all. And so that's that example for you there.